right, so now I'm going to do a more comprehensive example for this problem 161 in chapter 6. I actually personally remember doing this problem in dynamics however many years ago, and I remember taking a really long time because there's a lot of stuff that can go wrong. So I thought I'd at least teach you the basics of how to do it because it is on your homework. There's not a lot of equilibrium problems, so I wanted to give you what there was. So I usually go over this in class in some detail. The beginning is going to be maybe a bit more than you need on the background of virtual work problems, but then we'll get into more practical solutions. All right, so let's start by thinking about kind of even a simpler case for static equilibria. So for static equilibria, what you can have is you can have a simple system like this, and where you have some mass on a spring and some variable of interest x. And if you plot x on one axis and the spring potential energy on the other axis, you get this nice parabola here, 1/2 kx squared. And it increases, right? When x is 0, let's say x is measured from the uncompressed state, then as it increases, the potential energy increases. And now for gravity here, because we've defined x going down, as x decreases, the gravitational potential also, or as x increases, the gravitational potential decreases. So we have this line here for our mgh, but now h is negative x. And now if we add those up together, right, we would get some potential energy, and we could still be plotting that in terms of x. But it would start out, pretty linear like this when this is small, and then it would increase, right? Because the parabola is going to take over. So at some point there's going to be some local minima here, and that is going to be your equilibrium position statically. And at that position, you could say that the partial derivative of the spring potential energy is going to be equal and opposite to the partial derivative of the gravitational potential energy. And so this kind of plot is where this virtual work thinking, I think it really helps you to think about how this works. But now we want to think about in an accelerating reference frame. This is just statics. Now in this problem here, we have these masses and they will have some acceleration, right? They'll have some acceleration here towards the shaft. So if we were thinking about the forces on this, we could draw these link forces, but we could also think about that ma, the acceleration, being on the other side of the equation, right? So like we've been writing F equals ma, just as easily could be sum of the forces minus ma equals 0, right? So we can flip this ma on either side of the equations. All right. So in this problem, we're gonna do that. So the shaft, if you look at the energy of this problem, the shaft is gonna be spinning, and that's going to change this angle theta. So if you can imagine when theta equals 0, the mass is right along, or just this small quarter-inch offset from the rotating shaft. As theta increases, the mass here gets further and further away from the axis of rotation. And you can kind of picture this happening if you spin it up really fast. That spring here is going to get really compressed. And so if we picture these different states, and we're going to think about this theta as our kind of variable of interest, and we're thinking about, okay, what is the energy here in this problem? I'm going to use this thinner pencil because I feel like that pen changes the focus of the camera. So, all right, so here we think about the energy here. So the spring is obviously going to have some energy. And then there's going to be a change in the kinetic energy. So here the kinetic energy is going to be high because the mass is now moving further away from this radius, right? So it's going to be moving faster. And the spring is also going to be more compressed. So the spring is going to be having more potential energy. And that energy comes from the work that it takes to rotate this shaft. right? So the faster you rotate the shaft, the more energy you put in here. And we want to, but we don't want to be calculating like the work that goes into this to get that. In part for a couple of reasons. We don't actually have enough information, as we'll see in a minute, but also because we're learning this method. So for virtual work methods, we're looking for equilibrium in these kind of dynamic reference frames. So we're looking for things in terms of rotating coordinate system, and then the work done by that rotation, and a small increase in that is going to result in a small increase in energy into the spring. And so instead of thinking about, just for a minute, imagine instead of thinking about that kinetic energy term, we're going to have that work done against the acceleration, because we know that they're sort of equivalent. So, right, the work done against that acceleration, or against this force, right? So if we think about work as a force over a distance, the integral, right now the force is this negative ma, and the more work we do against that, that's going to result in changes to the potential energy of the spring, and maybe some relative kinetic energy, but we're not really going to worry about that, because at a dynamic equilibrium, right, a small change here, right, like this, like we're not going to have any theta dot terms here, because theta is going to be constant. All right. And now, so we could also then swing this term, because we talked about how the change in kinetic energy kind of has that v dv term, which is the same as ads. So we could swing this around, and we could be saying, okay, so now this change is going to be equal. This change in kinetic energy is going to equal the change in potential energy here. All right, or we could just as easily say, really, that from an equilibria, some virtual change, even if it doesn't actually happen in kinetic energy, plus some virtual change in potential energy, if we sum those together, that's going to be equal to 0. And how can we really picture that? You don't need to go through this for every time you solve a problem, but I just thought it would be helpful. So let's picture for this problem the potential energy. What does that look like? So for this problem, we can have theta between 0 here when it's flat like this, and 90 degrees here. And here the potential energy is going to be higher because, like, that spring is going to have some x. Well, actually the x is, let me draw that differently. The x goes to, so let's draw it for the theta picture. The x goes to the bottom here. X, right? So this is the displacement of that collar, because it starts out at 0 when this is 0. So when theta is not 0, there'll be some x in this direction. All right. So as x increases, when it's 0, the spring is uncompressed, and so there's no potential energy of the spring. And then at 90, it's at its maximum. We can calculate what that is, because we have the potential energy is 1/2 kx squared plus 1/2 times whatever x is. So in this case, x is going to be 3 minus 3 cosine theta, and we can square that. And then they give the stiffness as 5. Oh wait, there should be over 12 here somewhere. It's 5 pounds per inch, so that's why there's already one here. Okay, so but anyways, the potential energy is there's a 2 here. That's from this 1/2, so we gotta divide this by 12. But so there's a potential energy here, and we want it to be in pound-feet instead of pound inches. But so it's going to increase, and there we go. Let's think about the kinetic energy. All right, so the kinetic energy here for these rotating masses here is going to be our 1/2 mv squared, where we're talking about v bar, plus 1/2 I bar, And now our omega for these would be n squared. And just because there's 2 of them, we'll multiply this by 2. So we'll get to more of this in a minute. It turns out like we don't have the information to calculate this, but it doesn't matter. So here now we can think about what is the velocity of the center of mass, and it's going to be some omega across r plus v rel. And so then that omega would be that n, and then here's our r would be this distance here from the shaft to the center of mass. So it's that 1/4 inch plus this. So, okay, here we have our R, and I've divided that by 12 just to keep things consistent. And so, okay, so that's also going to be increasing because it's going to be smallest when it's when the masses are real close to the shaft. And oh yeah, so again, you might argue that, oh, shouldn't there be some velocity based on theta dot times the link length, right? Shouldn't there be some change? Yes, there would be this. It would be normal to the link, like if you're looking at the vector velocity. But for virtual work problems, you don't have to worry about the rates of change of theta because we're thinking about equilibria, where theta is going to be constant and we're going to be able to read it from the needle. It's not going to be like wiggling around, right? We're going to be able to read this from the needle. So we're looking for an equilibria point where theta dot is 0. So but this value, if you thought about how fast this block was going, this would be into the paper. And so this is the one we're going to use. So if we think about our kinetic energy, we have 1/2 our n squared over 12 squared plus this times this radius, and that would also be squared. And then if we plot that, we would also have to add this I bar term, but it's not going to be changing with respect to theta, right? Like all of this I term is the same, no matter how far away those blocks are. So now if we want to see the equilibrium point, we can think about it at the equilibrium. Then we plot the Lyapunov function, which you'll learn more about in advanced dynamics because dynamics is so fun. You should definitely take advanced dynamics. So here we're going to take our PE minus our KE terms, right? And so now if we added these up, now there would be this dip, and that would be at the equilibrium theta. And at that time, the partial derivative of the kinetic energy would be equal and opposite to the partial derivative of the potential energy, right? And wherever that's true, then there's going to be a local minima because the derivative at a local minima is always going to be 0. All right, so here for this equation, we're going to have some 2ma virtual work in S times or plus kx virtual work in x. And these are my pro tips for all of these virtual work problems. I think you should make sure you draw this virtual change in S. It has to be in the same direction as your acceleration, right? So in this case, yeah, that's inward toward the shaft. And then draw X from the undeformed spring length. So let's go ahead and do that. All right, so here's our problem. And here, I might have to switch to, let's see, is this visible? I thought pencil might not be visible. So here is our change in S, because it has to be in the same direction as our acceleration. So this is accelerating inward. And then here, so this is very small displacement, but this is going to be X, right? So because we know that when beta equals 0, then theta equals 0. So when this is all perfectly stretched out, we know that this is aligned. I feel like that's another thing that the first time I saw this problem, it took me a minute to figure out, like, because they don't really tell you that this is aligned with this when they're equal, but that is the assumption. All right, so we've got our x and our s defined here. And now we have to relate things to this beta term as well. So how do we do that? Let's take a look. And here we're going to have our beta equals 0 when theta equals 0. So it's just going to be beta times, so we're going to have the beta here, and we're going to have the sine of the beta, because we want this component times that 5/8. It's going to equal x. And so that means for this problem, and we know 15, we can calculate x. All right, so we're going to know some x here. Now, how does that relate to our other problem? Oh, and don't forget that at least in this part, they want the answer in revolutions per minute. So you can go ahead and convert that to radians per second. Okay, just so that you know that this is the answer we're looking for n. All right. What else is it possible to mess up on this problem? There's a lot of things because it's English units, but let's just remember why we're using virtual work again for this problem. There's multiple bodies. We know it's at some dynamic equilibrium position. So that's sort of a hint that maybe this is easier to solve this problem with virtual work. So we can write out our virtual work equation from the book. We have our virtual change in work is going to equal our sum of our MA dot virtual change in S plus any virtual changes in I alpha to virtual change in theta. Now this theta here is not the same as this theta. This is just the form of the formula, so it has to be in the same direction as any angular acceleration, but there is actually no angular acceleration, so you know, we're gonna be looking for when n is constant. So we don't have to worry about that term. What other terms we got here? We got sum of mg virtual change in h. If we were in class, I'd be asking, okay, do we have to deal with this term? And I'd let you think about it. But since we are virtual, this term we don't need to worry about. And the reason is because the shaft is rotating, and to get any useful reading, we have to imagine, and it's rotating pretty quickly, we have to imagine that this needle is not moving with every single turn of this mass mechanism. So the only way this problem makes sense is if we can ignore this term, and that's small relative to spin. And if you kind of like peek at the answer here, this is pretty fast, and these are pretty small dimensions, so I believe that. All right, so now, but we do have a spring term here where we're going to have our kx virtual change in x. All right, so as always, this term is equal to 0 because in our rotating reference frame, we're not adding any other work. Like the shaft, in order to rotate, is doing work, but that is all happening relative. If you were in some rotating coordinate frame, rotating with these masses, you would just be like, oh, there's this weird force pushing me away from the center. Like you might not know that, you know, that you wouldn't measure that as work. And so that work is already kind of accounted for in this term. All right. So let's keep going here. Now we need to just relate these virtual changes in x and virtual changes in s with some other variable that we care about, and let's pick theta for this. So we can say x is equal to 3 inches, and then we're gonna so So we want this little change in x. So it's the 3, which is the unstretched length, minus whatever this is doing to that. So that would be 2 times 1.5 times, and then we want this component here, so it's a cosine of theta. All right, and so we can just take the variation of that. I keep forgetting what to call this. This is variational calculus, so we can say this is the variation of x equals, now we've got 3 sine theta times the variation of theta. And then, oh, this would be a negative, but the derivative of sine is negative, so this is going to be positive. And that makes sense because now if you increase theta, you're actually stretching the spring more. So it makes sense that there's a positive and a positive. All right, so now what else do we need? We need this ds term. All right, so here we have we can actually draw this here. We could draw, if there was some variation in theta, where this angle here is going to be our change in theta. Oh, sorry, you can't really see that. Then this difference, this length change, would be L variation of theta. And now we want this component, the component that's actually, it's not in the same direction, it's in the opposite direction of acceleration here. So this angle is theta. If we drew a line here, this angle would be theta. Can't really see this very well. And then also you could convince yourself, right, that this angle up here is theta. So what we want is that variation in S is going to be negative 1.5 times we want the cosine of theta, variation, not like that on the screen, variation in theta. All right, so once we have this, and you kind of really want all of these in inches, so let's divide by 12. Or they're already in inches, we want them in feet. Okay. Yeah, so now we just have to put everything together. So we're going to have 2 of these terms because there's 2 masses, so don't forget that. One of the other many ways we can mess this up. So we have 2, and then the mass is 12 ounces, so that's, the weight is then 12 over 16 over 32.2 because we want it in slugs. That's our mass term. And the acceleration is going to be our angular velocity squared times the radius. So the angular velocity is what we don't know, that's n, and the radius we do know is 0.25 plus 1.5, and now we want the sine of theta here. And we're going to divide that by 12 to keep things in feet. All right, so this is our acceleration. So I'm going to show you that, right? Here we go. And we're going to have, we need this ds term, and so that is 1.5 cosine theta over 12 d theta, and we're not going to forget the negative sign, we'll put that here. Okay, and all of that plus, now we're going to have our spring stiffness, which is 5 pounds per inch. So that means we need it 5 times x in inches, 3 inches minus 2 times 1.5 inches times cosine theta. And then I'm not using the divide by 12 here because this is already in pounds per inch. And then what do we finally need? We need our variation in x with respect to theta. So that's 3/12 sine theta variation in theta. And all that equals 0. And now because we have a variation in theta and another variation in theta, they will cancel. And so we can just solve this. And to do this, of course, you first need to find theta. So for this problem, I found theta by setting x here equal to x up here with our beta terms. So in this problem, for these values, theta equals like 18 degrees. And then when you solve this out, you will in fact get 13.9. Okay, good luck. Please feel free to ask me questions in the comments.